Now independence of sigma algebras. So now we are only talking about independence of events and collections of events. Now we will talk about independence of two sigma algebras and then eventually independence of a collection of sigma algebras. Okay. Now see, now you are talking about a probability measure P, right. All this independence is being discussed with respect to this probability measure P, right, and this P is defined on which one? F, right. So if you want to speak about independence of two sigma algebras, let us say F1 and F2 on omega, you have to you can only look at sub sigma algebras of F, because P is only defined on F, right. So we will only discuss, it is not even meaningful to discuss P may not be measured on maybe not be defined on some other sigma algebra, right. So we will say let F1 and F2 be sub sigma algebras. So what does that mean? Huh? No, I am looking at the sub sigma algebras of F. I am asking what that means. So by sub sigma algebra I just mean, see, F is some collection of subsets of omega. F1 is a sub sigma algebra, means F1 is contained in F. So every subset contained in F1 is also an element of F. Similarly, every subset contained in F2 is also an element of F, but they are both sigma algebras. Okay. So if you want, so can you give me some example of a sigma algebra and a sub sigma algebra? Yes. So that is a very trivial example, right. You can take phi omega to be one sigma algebra, which is a sub sigma algebra of phi omega a complement, right. That is a very simple example. If you want to be a little more complicated, you can take, let us say omega equal to 0 1, let us say 2 power omega is still a sigma algebra, 2 power omega is a sigma algebra, but Borel sigma algebra is a sub sigma algebra of 2 power omega, right. Actually in your homework you are encountered but in the first homework I think, right, there was the collection of all subsets of 0 1 which are countable or have countable complements. Remember we called it F3 or something in your homework. That is a sub sigma algebra of Borel sigma algebra, you think about it. Okay, it will only have countable sets and sets with countable complements. It will be a sub sigma algebra of Borel sigma algebra. Okay, so these are just examples. Okay, good. So you are okay with this? You have two sub sigma algebras of F, and you want to speak about the independence of these two sigma algebras. Okay, remember P is defined on F, so P is defined on elements of F1 and F2 as well, right. F1 and F2 are said to be independent if for any A1 in F1 and any A2 in F2, A1 and A2 are independent. Okay. So I have two sub sigma algebras F1 and F2, they are collections of subsets of omega. You pick any event you want from F1 and any other event you want from F2, right, it is completely up to you which one you pick. So no matter which one you pick, those two events must be independent events. If it is true for every such A1 picked from F2 and every such A2 picked from F1 and F2 respectively, then F1 and F2 are said to be independent sigma algebras. Okay. See, if you happen to pick null or omega, it will trivially hold, right. If you happen to pick omega from here and something else from F2, it will trivially hold. So, for phi and omega there is no problem, but the rest of the events the independence should hold. Okay. Is this clear?
Sir,
yes.
if probability P is measured for F, the same probability P can be applied to F1 and F2.
This is exactly what I said. So, F is so P is defined on F. So, no matter which one you pick from F1 and which one you pick from F2, P is defined on, see F1 and F2 are after all sub sigma algebras, right. So, measure defined on F is also defined on F1 and F2, right. So, all of this is independence with respect to that measure P defined on F, okay. Which is why I said, see, if these were not sub sigma algebras, if they were some other sigma algebra which are not necessarily contained in F, then you may not be able to define P on it, which is why I said sub sigma algebras of F, understand. So, if I take F as, say I cannot take F as let us say Borel on 0 1 and take F1 as something bigger, because Lebesgue measure for example may not be defined on some bigger sigma algebra, right, that does not work. So, you have to have sub sigma algebra, okay.
So, is it necessary that F1 and F2 have the same sample space as F?
Yes. So, they are all sub sigma algebras as F.
So, if just an intersection I take sample space of F1 and intersect with any other element in F2, there will be anyhow disjoined. There will be some.
No, that is not true. So, I do not understand your question. So, F is, see, F is a sigma algebra defined on omega, and F1 and F2 are sub sigma algebras.
So, do the F1 and F2 have the same sample space as that of?
Yes, because they are sub sigma algebras of F.
So, if you take sample space of F1 as one event and then it is intersected with
No, the sample space is omega. The sample space is always omega, right. They are not on different sample spaces. In fact, they are on the same. See, the sigma algebra F and the measure P are fixed, and I am just looking at sub sigma algebras F1 and F2 of F.
So, suppose if I pick the omega from F1 and I am intersecting with other elements of F2, there will be anyway some joiners, anyway some.
Yeah, but they will trivially satisfy independence, right. So, let us say A1 you pick as omega, right. So, in particular F1 is a sigma algebra, so it must contain omega, right, and A2 you pick as whatever you want, then you will get probability of omega intersection A2, which is just A2, equal to probability of A2. So, that is very trivially satisfied, and similarly for null set, right. So, these are not problem creators at all, right. So, if at all this fails to hold, it will fail to hold only on some other non trivial subsets, right. Okay. So, independence of two sigma algebras means all these events here are independent of all these guys here, anything you pick here and anything you pick here are independent, right. Finally, I will just put one more definition. Let Fi I belongs to I be an arbitrary collection of sub sigma algebras of F. So, the next logical step is to move to, see, we went from 2 events to some collection of events. Similarly, we are going from 2 sigma algebras to some arbitrary collection of sigma algebras. This I may be finite, infinite, even uncountable probably, right. They are all sub sigma algebras of F. Okay. What do you expect now? What do you think the definition should be? You pick any AI from Fi, any whichever way, right. So, from each of these AIs, pick in each of these Fi's, you pick any AI you want, then you will end up with a collection of events AI indexed by capital I, then I will apply this definition, that is all. Okay, that is, it is a very simple definition. These FIs are said to be independent sub sigma algebras F set, right? Yeah, okay, said to be independent if for any choice of AI in Fi, I in I, we have AI I belongs to I are independent events. Okay. So, you are given some arbitrary collection of sub sigma algebras of F, right. From that collection, each of those sigma algebras will contain phi, omega and a bunch of other subsets, right. Now, from each of those sigma algebras, you pick any AI you want, right. No matter which way you pick this AI, if AI I belongs to I are independent events, then this collection of sigma algebras are said to be independent sigma algebras. Okay. And what is the meaning of this? I have to go to this, right. So, I have to select, this could be a infinite collection or even an uncountable collection. So, I go back to that definition and say for every finite I naught I have this holding. Okay. So, you have this hierarchy of definitions. Okay. Are there any questions? So, this is very, it is very important to digest these definitions. Okay. You should really internalize them, because this will come up when we do random variables and so on, right. We will define independence of random variables in terms of these notions.
That particular FI alone.
No. See, you are given a bunch of sub sigma algebras which are indexed by I, right. So, this is one sigma algebra, this is one sigma algebra and so on. From each of them you pick any event you want, right. So, no matter which way you pick it, that collection you end up with, which is also indexed by I. See, after all, this AI is picked from Fi, right, and no matter which way you pick this AI. So, which is why I have said for any choice of A in Fi, I belongs to I, this collection is an independent collection of events. And independence collection, this is what I mean by AIs are independent. Okay. Any other questions? So, let me just give an example. So, I just want to make one general remark which may not be so relevant to you. See, the fact that you are given some, let us say you are given some arbitrary collection of sigma algebras, right, it may even be an uncountable collection of sigma algebras, right. The fact that you can pick one, so what am I doing? I am picking one AI from each of these FIs, right, but if this is an uncountable collection, can I even do it, right. So, this is called axiom of choice. You assume that you can pick one element from any arbitrary collection, arbitrary set, right. So, all of this measure theory, probability and all assumes this axiom of choice to hold. Okay. So, because you will ask me, right, oh, what if I give you some uncountable collection of sigma algebras, how do I pick one from each of them? You will never exhaust it, right. So, there is no notion of time or picking or any such thing, it's just assume that you can do it, right. This is a consequence of this axiom of choice. Okay, so again, so to give you an example of this, so I have maybe 10 more minutes. Let us see. So, AI, so as usual AI is the event that the ith the coin toss model. Okay. So, now again AI is the event. So, omega equal to 0 1 power infinity, AI is the event that ith toss is heads. Okay. Heads is 0. Okay. Now, let me see, let me define so let CO equal to the collection of all. So, I am defining a collection of events CO as those AIs for which I is odd, okay, and CE as the AIs for which I is even. Okay. So, what I mean is I is 1 3 5 and so on, here I is 2 4 6 and so on. Okay. The claim is, so claim let FO equal to sigma of CO and CE is equal to sigma of FE equal to sigma of CE. Yes, FE equal to sigma of CE. So, FO consists of all those events which only have to do with the outcome of the odd tosses, okay, and FE is a sigma algebra which consists of the outcome of which can be decided only by the even tosses. You can show that F naught and FE are sub sigma algebras of what we called F, okay, it requires a proof, and you can show that F naught and FE are in fact independent sigma algebras. Okay. So, this is an example to show you can, so can show F naught F. So, these are sub sigma algebras of F and under the measure P F naught and FE are independent. So, in order to do that, what do? You fix any event B which is a, so any event pulled out of here and any other event pulled out of here must be independent, right. So, an event, so the core of the argument is the following: any event pulled out of here will only depend on the outcome of the odd tosses, right, and any event pulled out of here will only depend on the outcome of the even tosses, right. But you know that, this fact, right, that the across these indices the tosses are independent, right. So, you have to put these two things together, make it precise. You can show that f naught and f e are independent sigma algebras. Okay. So, this is something again you should try. Okay. I mean, I am saying this in all seriousness, it is not all that trivial. It's the definition is easy to understand, but executing it will take some work. Okay. Any questions? Okay, so I think I should stop here. See, I will just mention one fact. See, okay, so I will not actually, I will not, so I will say this on another occasion. I will just state at this point that if you want to verify the independence of two sigma algebras, see, sigma algebras are fairly complicated, right? Let's agree on that. They have all sorts of countable unions in them, right? So, if you take Borel sigma algebra, it consists of several complicated sets, right? So, if you have to verify the independence of two sigma algebras, you have to go about pulling out all sorts of complex sets from here and show that independence holds, right, that the measure products out on all these complex sets in the sigma algebra. However, there is a saving grace. In order to show that two sigma algebras are independent, it is enough to show that independence holds on certain generating classes alone. Okay, I will just roughly put it at that level. So, if you have a collection of sets which are closed under finite intersections, only finite intersections, no complement, no countable union, anything, right. So, a collection of sets closed under finite intersections, if you verify independence under those, for those collection of events alone, it is enough to say that the sigma algebras generated by these collections are independent. Okay. I will state this properly as a theorem when we move on to random variables. Okay. But at this point I want to say that you do not have to worry about really checking independence for all sorts of complicated sets, Borel sets and all these complicated subsets that exist here. It is enough to verify on a certain generating class. Okay. These generating class which are closed under finite intersections, okay, they are called pi systems. Okay, so that is it. There is a, like sigma algebra, there is a word for it, pi systems. So, independence under pi system is enough to show independence of the sigma algebras. Okay, I will state this later. Just make a mental note now that it is not as difficult as it seems. You do not have to pull out all sorts of complicated events from the sigma algebras and verify. Okay, I will stop here.